Okay, let's continue with the Descartes' rule of signs tool. Okay, we're going to do this one. F of f located at x is equal to x to the fourth power plus x to the third power minus 53x squared plus 159x minus 108. Now in order to first get the possible roots, we're going to start off with the rational root test, like we did with the other problem. Okay, and if we do the rational root test, we have to get the rational root test gives us all the possible roots, and when we do the rational root test, we get the factors of 108, which is the constant, and we need the factors of our leading coefficient, which is 1. So factors of 108 and factors of 1. So let's get the factors of 108. The factors of 108 are plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 9, plus or minus 12, plus or minus 18, plus or minus 27, plus or minus 36, plus or minus 54, and plus or minus 108. The factors of 1 is just one factor, plus or minus 1. So we divide the factors of 108, all divided by the factors of 1, and anything divided by 1 is itself. So the factors of the possible roots will be all of these factors above here. And we have a total of how many factors? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We have a total of 24 factors that we have to test in order to derive at some possible roots. Now, we're going to shave this down by using the Descartes rule of sign tool, because these are just too many factors to divide into our function by the synthetic division. So here's a Descartes rule of sign chart that you can write down. It's going to be your template that you should always use whenever you are finding the zeros or roots or solutions of polynomial functions. So you're going to have your first you're going to find f at x, right? And then you're going to find f at 0. What you're doing is you're finding the sign changes of f at x and f of negative x, right? And the number, what is going to happen, you find the signs of them all, signs, and then you're going to get the number of times the sign changes, okay? It changes over. And then the number of real roots that you will get, right, will be equivalent to the sign changes, or the sign change, the total number of sign changes less than that number of sign changes by an even integer. And usually that even integer is 2. So if you have 3 sign changes, right, you have a number of 3 real roots, or 3 minus 2 roots, which is 1. So 3 or 1 roots. So let's do this one. F at x, right? F at x. The number of sign changes of f at x, the number of signs we have positive, positive, negative, positive, negative. So we're going to put that in there. Positive, positive, negative, positive, negative. And the number of times the sign changes, if we look at the signs, it's positive, positive, the sign doesn't change. Here it changes once. And it changes it again to positive. That's twice. Then it changes again to negative. Okay, so it changes 1, 2, 3 times. So the number of real roots that we have are 3, or 3 minus 2, which is 1, or 1 positive real roots. Okay, now we're going to look at f at negative x. Right? If we change all the x's of f at x f at x into negative, we're gonna x add x to the fourth power, change x, put a negative into x in there, it will come out positive. Okay, so positive. If we put x in f at x here, x cubed, negative x cubed will be equal to the positive sign here would change into negative sign. Good. So here, if we put a negative in x here, x squared, negative x squared will be a negative times negative is positive, right? So the sign doesn't change, it stays the same, right? And if we put a negative into this x here, negative x times 159, this positive will, if we multiply into negative x, will change into negative, right? So it will change from positive to negative. And there's no sign here, so this sign here stays the same, negative 108. So the number of the signs in f at negative x are positive, negative, 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 negative. So let's put it in. Positive, negative, 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 negative. So what are the number of times of sign change? What are the number of sign changes? We have positive, and it changes once. It doesn't change again. So there's only one sign change. And the number of real roots are, or is, in this case, is one negative real root. You can't go below that. Right? And so the number of cases that we have here, we have case number 1. We have a total number of 3 positive roots or 1 negative real root, and the total number of go down, the total number, the highest power we have is 4, so we're gonna have 4 solutions. We count the number of real roots we have so far. 3 plus 1 is 4, so we have 0 complex roots for a total number of 4. Great, that's the 4 solutions, that's what we want. Or another scenario, case number 2. Case number 2, we have 1 positive, okay, 1 positive real root, and 1 negative real root. And if you look at the top again, we had the highest power is 4, right? 4 to the 4th power. So we have total number of 4 solutions. We have 1, 2, right? 1 and 1 is 2. So we have 2 complex roots for a total number of 4 solutions. 4 solutions. Okay. Now let's look at the columns. The positive real number column. Let's look at the number of negative real number column, and let's analyze that there are more. If we go with the positive, roots, right? You're gonna get either 3. You're gonna get either 3 or 1 guaranteed positive real roots. And if you look at the negative real numbers of possible solutions that we have, that we got from the rational root test, you're gonna get from that, if you test them, a guaranteed 1 or 1 negative real roots, right? So the more efficient, I personally think the more efficient roots to go after are the positive ones, because you guaranteed either 3 or 1, right? Now we're gonna test, so we're gonna go after the positive real roots, and once the root is found, we're gonna use a shortcut, right? We're gonna use a shortcut, break down the power from 4, break down the 4 to the 3rd power using the shortcut method, and break down the cube to a quadratic, a square. And once we have arrived at our quadratic, we're going to use the factor method or the quadratic formula in order to arrive at our two missing roots. So let's test. Let's do our test. Okay, first test, we're gonna test for some of the, well, let's write out the roots that we have now, because we just shaved down half of the roots. Before we had 24, we just shaved down half of that, and we're gonna have 12 roots. It's gonna be 1, 2, 3, 4, positive 6, positive 9, positive 12, positive 18, positive 27, positive 36, positive 54, positive 108. So the Descartes' rule of sine tools shaved down half of what we had before, and they're all positive. Okay, let's test. Let's test for this test x equals to 1. Okay, and if we look at our function, we had originally it was x to the 4th power, x to the 3rd power, minus 53 x squared plus 159x minus 108. Okay, we're gonna just write down our coefficient. 1, negative 54, 159, and then negative 108. Draw our L-shaped box thingy. 1, okay, and then bring down your 1. Okay, and 1 times 1 is 1. 1 plus 1 is 2. 2 times 1 is 2. 53, negative 53 plus 2 is negative 51. Negative 51 times 1 is negative 51. 159 plus negative 51 is 108. 108 times 1 is positive 108. Okay, negative 108 plus 108 is 0. Now, since the remainder is 0 there, x equals to 1 is a root, right? A root of that function, right? And it's also a factor. So we're gonna turn our answer here, right, which is our q of x, our quotient, into a polynomial. And in order to turn it into a polynomial, we have to look at the original function, the power of the original function, and the power was a power of 4. So our quotient, when we're going to break it down, when we use this shortcut, we're going to break down our quotient, our answer. It won't be 4, but it will be 3. So let's first write down our divisor, x minus 1, right, times x cubed, right, plus 2x squared minus 51x plus 108. Ran out of space there. Okay. Now we want to get down to a quadratic, so we're going to keep testing with our numbers there on top. We already tested for x equals to 1, so that crosses out, right? We're gonna test for other functions. I mean, we're gonna test for other numbers. So let's test for x is equal to 2. Test x is equal to 2. Okay. So, and this time we're not gonna use we're not gonna put in the original function x is equal to x to the 4th power, right? We're going to test for this function here using our shortcut, x cubed plus 2x squared, right, minus 551x plus 108. We got to make sure that everything is in all the powers are in descending this order, right? So cube, we have 3, 2, x to the invisible 1 power, right, plus 108, right? Great. So we're going to put all the coefficients in, 1, 2, negative 51, and 108. And I like to put the dots before the last number, right? Yeah. And we're going to draw an L shape. Great. And we're gonna divide this by 2. Great. Okay. Bring our 1 down. And a 1 times 2 is 2. Okay, 2 plus 2 is 4. 4 times 2 is 8. Negative 51 plus 8 is negative 43. Negative 43 times 2 is negative 86. 108 plus negative 86 is 22. Aha! Okay, now this remainder, since this remainder is not 0, x equals to 2 is not a root. Okay, so we're gonna get rid of that and try another one. We're gonna test for x is equal to 3. 1. Okay. And then bring down your 1. Okay. And 1 times 1 is 1. 1 plus 1 is 2. 2 times 1 is 2. 53, negative 53 plus 2 is negative 51. Negative 51 times 1 is negative 51. 159 plus negative 51 is 108. 108 times 1 is positive 108. Okay, negative 108 plus 108 is 0. Now, since the remainder is 0 there, x equals to 1 is a root, right? A root of that function, right? And it's also a factor. So we're gonna turn our answer here, right, which is our q of x, a quotient, into a polynomial. And in order to turn it into a polynomial, we have to look at the original function, the power of the original function, and the power was a power of 4. So our quotient, we're going to break it down when we use this shortcut. We're going to break down our quotient, our answer. It won't be 4, but it will be 3. So let's first write down our divisor, x minus 1, right, times x cubed, right, plus 2x squared minus 51x plus 108. Ran out of space there. Okay. Now we want to get down to a quadratic, so we're going to keep testing with our numbers there on top. We already tested for x equals to 1, so that crosses out, right? We're gonna test for other functions. We're gonna test for other numbers. So let's test for x is equal to 2. Test x is equal to 2. Okay. So, and this time we're not going to use we're not going to put in the original function x is equal to x to the 4th power, right? We're going to test for the this function here using our shortcut, x cubed plus 2x squared, right, minus 551x plus 108. We got to make sure that everything is in all the powers are in descending this order, right? So cube, we have 3, 2, x to the invisible 1 power, right, plus 108, right? Great. So we're going to put all the coefficients in, 1, 2, negative 51, and 108. And I like to put the dots before the last number, right? And we're going to draw an L shape. Great. And we're going to divide this by 2. Great. Okay. Bring our 1 down. And a 1 times 2 is 2. Okay, 2 plus 2 is 4. 4 times 2 is 8. Negative 51 plus 8 is negative 43. Negative 43 times 2 is negative 86. 108 plus negative 86 is 22. Aha! Okay, now this remainder, since this remainder is not 0, x equals to 2 is not a root. Okay, so we're gonna get rid of that and try another one. We're gonna test for x is equal to 3. Okay, same thing. We have 1, 2, negative 51, 108. Okay, for an L-shaped thingy. Divided by 3. Okay, bring down our first number, which is 1. Okay, 1 times 3 is 3. 2 plus 3 is 5. 5 times 3 is 15. Negative 51 plus 15 is negative 36. Okay, negative 36 times 3 is negative 108. Aha, it's a 0. Our remainder is 0. And since this remainder is 0, x equals to 3 is a root. So we have two roots. We have x is equal to 1 is a root, and we have x is equal to 2 is a root. So we're going to bring down so we're gonna look at the quotient here. The quotient, the answer was right here. Q of x is this. And we're gonna turn our answer into a polynomial. In order to turn it into a polynomial, we're gonna look at the answer the function we just divided, which was this one over here. The highest power is 3, so this is gonna be 2. So great. Let's bring it down. Let's bring down x minus 1, right? We're going to bring down x minus 3. And then this is going to be x squared plus 5x minus 36. Okay. And look, we have brought our problem, our function, our whole thing down to a quadratic. And now that we brought it down to a quadratic, we can do one of two things. We can factor it, and or we can use the quadratic formula to get our two missing roots, two missing solutions. And luckily we can factor this. The factors will be x. It will be x minus 4 times x minus 1. X plus 9, I'm sorry. X minus 3, x minus 3 times x plus 9 times x minus 4 times x minus 1. Good. Those will be our 4 factors. And so our zeros will be negative 9, 1, 3, and 4. So our zeros will be negative 9, 1, 3, and 4. Those will be our x-intercepts. Okay, and if we want to factor all of these, right? We have to get the multiplicities of all the x's, right? So the multiplicity of this one, x is equal to 1, x will be equal to 1, right? The multiplicity of this one will be x equal to 1. The multiplicity will be 1. So this will be of multiplicity 1. This one will be of multiplicity 1, right? And this is x equal to 4. This will be of multiplicity 1 again, because the power here is invisible 1. And this one is x equal to negative 9. It will also be of multiplicity 1. And if you want to graph it, remember the first thing we need to do, we need to know our arms, right? And we look at the original function. The original function was x to the 4th power. And the power of 4 is even, and the function is positive, right? So since it's positive, we're going to be facing up left and up right. So now that we have our roots, we're going to erase this. Erase all of this. We know that our roots are of odd multiplicity, so we're good. Just remember that everything is of odd multiplicity. Okay, leave that down there. And let's put in our polynomial function, man. So our arms are up. First thing is our arms. They're up, all facing up, left, and up, right. Right. Our turning point, since we know that the highest power is 4, right? Our teapot will be n minus 1, which will be 4 minus 1, will be 3. Put a 3 in the hat, and we have how many odd multiplicities? We have 1, 2, 3, 4 odd multiplicities, and odds are strange; they cross over. So we put all 4 odds x's into it. Now we're going to draw a graph. Put a graph there. Big graph. All right. And we're going to put -9, 1, 3, and 4. And the last thing we have to do when we graph before we graph it, we have to find the y-intercept. And if we change all the x's into zeros here in this function, if we change all the x's to zeros, we're going to have f of 0 is equal to -108. Right. So our y-intercept is -108. Okay, great. So remember our graph is up left, up right, and when we read the graph from left to right, we have to also draw from left to right. So we start up left, we go down to our first magnet, which is -9. It's odd, so all our odds, since all our x-intercepts are odds, we cross over all of them. Okay, we don't stop and turn anywhere. So we go to our first magnet, then we go to our second magnet, which will be this y-intercept here. We go to the y-intercept, immediately go to our next magnet, which is going to be 1. We cross over, and we turn around to the next magnet, which is 3. Then we cross over again and go to the next magnet, which is 4, and we end up going all the way up. And that's how our graph should look like. You can go back, try this on your own, and go practice and see if you get the same thing. Again, it's good that you practice. Practice makes habit, right? And once it's habit, you can do it on your own and be confident and get 100% score on everything, hopefully. All right. Take care. Hope this helps.